Hi, my name is Todd Lammle, and welcome to Module 1, Internetworking. In this first part, we're going to talk about basic networking terms. We're going to talk about the difference between the term router, bridge, and switch, collision and broadcast domain, as well as the devices used in an internet network, hub, bridge, bridging technologies is really what we use, switching, LAN switching, routing, logical networks, the term IP, bits, bytes, megabits, and so on. So let's get started on basic networking. So what is a network? Is it a physical boundary? Is it a building? Is it a city? Is it a country? It's none of the above. Is it a laptop? Is it a PDA? Well, it's all of the above, actually. The fact is we have a corporate office, we have remote offices, we have home users. We certainly have mobile users, and we're going to see more of those as the years go by. Let's talk about some basic terms before we get started. What is a bit? A bit is one digit, either a 1 or a 0. It can't be anything else. It can't be a 2 or a 3. That certainly would change things, wouldn't it? But if we happen to have 8 bits, we now have a term called a byte. If we have 1,000 bytes, we have something called a kilobyte. If we have 1 million bytes, we have a megabyte. 1 billion bytes is a gigabyte, and that's 8 billion bits. Now, to put this in perspective, if we're running 10 megabit half duplex Ethernet, which we used to for years and years and years, we're doing our network transfer at 1 bit at a time. This is why we want to run fast Ethernet or gigabit full duplex Ethernet. And we're going to talk more about those terms in the Ethernet Technologies Part 3 of this module. Now, the basic network is comprised of a few things. The first thing is naming conventions, logical addressing, and hardware or MAC addresses on a LAN. The naming convention is, say in this example, maybe Bob and Sally. It certainly could be something more complex, serverf.acme.com. But nonetheless, we have to resolve these names to a logical address to be able to communicate. And we would do this using something called domain name service. We certainly can use something called a host table, which is a static DNS basically, but we don't use that too much today. We'll typically use DNS to resolve host names to IP addresses. Now, throughout this module, you'll hear me use the term IP address a lot, and the fact is we don't have to use IP addressing. We can use any type of logical addressing that would work for us, IPX, XNS, AppleTalk, and so on, but it's pretty rare today to find something other than IP version 4. So in this example, again, the basic network here, we have what's called a hub. We'll see in the next few slides, just a multi-port repeater. It's going to take a digital signal and re-amplify it or regenerate it, depending on the type of hub, and send it out all active ports. Now in this case, Bob will send something to Sally, but he cannot send something to Sally using her IP address. He knows her name. That might have been resolved to an IP address, but since we're on a LAN, we still don't use IP addresses to communicate. We use hardware addresses, or what's called a MAC address for slang. So we have to get Sally's hardware address, and how do we do that? By using something called ARP, or Address Resolution Protocol. Now, ARP will be covered more in Module 2, TCP/IP. In this example, Bob can communicate to Sally because he resolves her name to an IP address, then to a hardware address. And he's connected together on the same LAN. Now, what happens if Bob and Sally are no longer on the same network? In other words, they're separated by a router, a layer 3 device, maybe called a forwarder at times. Now, Bob has to know her IP address. So he will resolve it to an IP address, her name, Sally, to 1.1.1.1, for example. Hopefully by using DNS or static host table, which would be crazy, but can be done. But he will send the packet where to get to Sally? First off, he can no longer use her hardware address because she was no longer on the same network. So Bob, knowing that she's on a remote network by comparing her IP address to his own, will see that she's on a remote network. So in this case, he will then send the packet for Sally to his router, which means it has to go on the local network, and the hardware address that he'll use on that LAN will be the default gateway address or router interface of his LAN. We have to be very clear and understand that Bob will never use a remote hardware address. He will always use a local hardware address even if the packet is destined for a remote network. A router also creates what is called an internetwork. Before we had a router, we just had a LAN or a network. Once we put a router in there, we have what's called an internetwork because we're using logical addressing. Now this is where your money comes from. Taking and building a physical network is only one half of the equation. You must then add a logical network on top of it. And this is where IP comes into play. And this is where you can make a career. Because if you can take a logical network and place it on top of a physical network, we have what's called an internetwork. And building an internetwork is probably the hardest part of networking. When we have multiple routers in our internetwork, we have to build what's called a map of the internetwork, or what we call a routing table. This is done by using a dynamic routing protocol. Now, we certainly can do it by hand by creating what's called static route tables, but that's a lot of work. Dynamic routing protocols are RIP version 2, IGRP, EIGRP, even OSPF, for example. And what these do is they build our routing tables for us. However, there's a cost for everything. They use more memory, they use more CPU cycles, and bandwidth for sure. However, they do build a correct map of the internetwork, and every router has the same map. Now think about your post office. If each post office in your city, assuming you have multiple post offices, they built their own map of the city. They built their own map of the city. If they did that, each post office would have a different map. And they'd never be able to deliver mail. And just like in your city, we can't have this on our internetwork. So by hiring a routing protocol to build our map, when I say hiring because they're taking overhead, to build our map of the city or map of the internetwork, we're going to make sure that each router has the same map of the internetwork or routing table. Let's be clear that IP does not communicate with these routing protocols, but it does use the information that these routing protocols build. So on each router, a routing table is built, and IP uses this as a map of the internetwork to deliver packages, or we're going to call packets, to a remote network. Let's talk about some internetworking terms. Collision domain and broadcast domain. A collision domain is created when I have two or more hosts on the same network sharing the same bandwidth. Now that means if two hosts communicate at the same time, there's going to be a collision. Typically we'll find these when we use hubs in our network, or we have multiple hosts connected into a hub, which is then connected into a LAN switch. Terms we'll talk about in a moment. What we want to do is have each host in its own collision domain. That's the best network today. Now let's talk about the term broadcast domain. We might have multiple hosts in our network, all in their own collision domain, but if one of those hosts sends a broadcast, whether it's an application broadcast, network layer broadcast, data link layer broadcast, it doesn't matter. Any broadcast will be forwarded to all collision domains. The broadcast will only stop when it gets to the router boundary, or what's considered your default gateway. So we might have multiple collision domains, but one large broadcast domain. This may or may not be good, and we'll talk about these terms more and more throughout this section. Let's talk about some internetworking terms that we use in our networks today. First off, we still use hubs. There's also bridges, but we call those LAN switches. But of course, in our wireless networks, we do have bridges still, data link layer bridges actually. And we also have the term router, which creates our internetwork. So let's go through each one of these terms one by one and understand what each of these devices do for us. Now, a hub is just a multi-port repeater. Before we had hubs, we had thin-net networks or coaxial networks with thin-net and thick-net. And basically, we used repeaters to extend the signal, which gave us greater range, and allowed us to put more hosts on each network. Now, when they came out with Twisted Pair, we were able to use hubs and, again, repeat out multiple ports at the same time. And we could connect hubs together, which would give us even more ports. We could have up to actually 1,024. Now, I've never seen that network, but I have read that in the specifications for Ethernet. Now, the problem is when one host sends a digital signal, no other host can transmit. And we'll talk about collisions when we get to Ethernet networking in Part 3. The other problem with this Ethernet network is that when one host sends a broadcast, every other host has to see that. So we're going to say that a hub gives us one collision domain and one broadcast domain. Now, this is not very good for corporate America today, but it's still great, okay, or it's still okay for our home networks or small networks, And we can still buy them pretty cheaply at CompUSA or Fry's or whatever your computer store is. So hubs aren't dead. We certainly can use them to help extend our network. We just wouldn't use them solely to build our network. Now, when we were using hubs to segment the network and break up collision domains, we used what was called transparent bridges or LAN bridges, and these each gave us a collision domain. So each port on a bridge was a separate collision domain. However, it's still one large broadcast domain. That means if a host sent an application layer broadcast, or a network layer broadcast, or a data link layer broadcast, any type of broadcast, that the bridge would forward this out all other active segments. So if we had a 4-port bridge, that would give us 4 collision domains, but 1 broadcast domain. Now, we don't see LAN bridges too much today, but we still see them in our wireless networks, don't we? What do we see today? We don't see bridges or transparent bridges, although we use bridging technologies. We use what? LAN switches. Now, we will use the term bridging or bridging technologies when we talk about our LAN switches because switches really are bridges with multiple ports, more intelligence, certainly more money. But if you go down to your local computer store, you will see that a LAN switch is comparatively priced with a hub. So why would you buy a hub when you can get a switch? Typically you wouldn't. Now, a multi-port bridge, again, is what we call a LAN switch today. And as we see in this slide, that a LAN switch gives us point-to-point connections, which means every port on a LAN switch is a collision domain. This is fantastic for corporate America, or even home use if you have a lot of data, right? Now, each port being its own collision domain means that a lot of devices can communicate on the network at the same time. Point-to-point connection. However, if one host was to send a broadcast, this would be forwarded out every port on the switch. Now, we can stop this from happening by using what's called virtual LANs. Okay, so a LAN switch, every port is its own collision domain, but it is still one large broadcast domain by default. Now, this brings us to a router, or layer 3 switch. We'll talk about the layers in Part 2 OSI reference model. But taking a look at this figure, we can see that this router has 4 interfaces, 3 LANs and a WAN. So routers will give us WAN services, something we can't get from a LAN switch. Now, off each router interface, we certainly could have a hub or a switch or multiple switches or multiple hubs or a combination of all. Now, each connection into the router is a collision domain for sure, but its main purpose is to break up what? Broadcast domains. So we have 3 broadcast domains in this figure. But you say, but I see 4 interfaces. You're right. But Cisco does not consider a WAN connection a collision domain or broadcast domain. It's neither, actually. It's a point-to-point connection typically, maybe a point-to-multipoint. But nonetheless, we don't consider it a collision or broadcast domain. So in this diagram, we see 3 collision domains, 3 broadcast domains. Now remember, to communicate on the LAN, we will not use a name like Sally. We will not even use an IP address. We will use the hardware address. If Sally, though, is on another LAN, we must use her IP address to send the packet to the router. The router will read the destination IP address and send it out to the street or LAN that Sally is on. Now, to communicate to Sally, though, we must translate that IP address to what? A hardware address. Just because we use the IP address to get to Sally, we still use hardware addresses on the local LAN. Now, we will use IP addresses to take a packet and forward it to Sally's LAN. But to communicate to the router, we will still use the hardware address on the local LAN. From Bob, in this example, to the router, we use the destination hardware address of the router. The router then uses the IP address to switch it to Sally's LAN. Then we use Sally's hardware address as a destination address to get the packet to Sally's host. Now, taking what we have learned in this module so far, how many collision and how many broadcast domains are shown in this figure? Well, if we take a look at here, we're using hubs, which means that we don't break up collision domains at all. The only device that segments and networks in this figure is a router. The router will break up both collision and broadcast domains. So the answer to this is 2 collision domains and 2 broadcast domains. Let's take a look at another figure and determine how many collision and broadcast domains we have. Well, the first thing we need to notice is we don't see a router in this figure. I see 2 switches and 6 hubs, multiple hosts connected into the hubs. Remember, the hubs do not segment the network at all, but the switches do, don't they? But by default, switches do not break up broadcast domains. Only routers do that by default. Switches only break up collision domains. So how many collision domains do we have in this network? Let's count the switch interfaces. I count 7 switch interfaces because the connection between the two switches is a collision domain. So we have 7 collision domains, and since we do not have a layer 3 device shown in this figure, we have 1 broadcast domain. So 7 collision domains, 1 broadcast domain is our answer. Which of the hosts can transmit simultaneously without causing collisions? The answer is only hosts A, B, and C. They're connected into their own switch port. Hosts D, E, and F are connected into a hub, which means they can only communicate one at a time. So also in this figure, can you determine how many collision and broadcast domains are shown? First thing to notice is we do not have a layer 3 device or router, so we have 1 broadcast domain by default. Switches do not break up broadcast domains by default, so we have 4 collision domains and 1 broadcast domain. Now before we end part 1 of module 1, let's take a look at one more slide and talk about, again, logical addresses and hardware addresses. This slide shows we have 2 routers, 2 LANs, and the 2 routers being connected through a WAN connection. So we have, looks like 2 broadcast domains and 2 collision domains connected together through, well, it could be a T1, frame relay, ATM, doesn't really matter what it is. But remember, on a WAN, we do not use hardware addresses. We will use some other type of encapsulation like HDLC, PPP, or frame relay. Now on the LANs, let's say that Sally is on one side and Bob is on the other, and they need to communicate. If Bob was to say from a DOS prompt, telnet Sally, the first thing that has to happen is name resolution. We must get Sally's IP address as 1.1.1.1 as an example. Once we have the IP address, Bob must then determine, is she on my local network or is the host on a remote network? Which means he must resolve it either to a local address or to his router. Those are the only 2 answers. That's the only 2 places that Bob can send this packet. Broadcast it out on his local LAN. It's a broadcast multi-access network, which is Ethernet. Or send the packet to the router or as his configured default gateway. Once he determines that Sally is on a remote network, he will look up his default gateway IP address in the registry and then need to resolve that to a hardware address because, again, we cannot communicate on the local LAN using an IP address. We must know the destination hardware address, in this case, the router's hardware address.